Okay, let's start by looking at our favorite system here, and let's reset the system and put some particles in there, put some more. So now we have a gas here. This gas has some properties, has a temperature of 300 kelvins, has a pressure about 0.5 atms, has a volume here, and has an energy, delta E thermal, right? So this guy has an energy. Now, suppose that I want to raise the temperature of this gas. One way to do that is by heating this gas, right? So let's add some heat. And now the temperature is raised, right? The temperature changed. So the gas had an initial E thermal initial, and then it went to an E thermal final. So the change in thermal energy is equal to E thermal final minus E thermal initial. And that is equal to what? Well, there was no work being done here because the volume didn't change. This is an isochoric process. So therefore, this is equal to the heat that we added, right? So delta E thermal is equal to the heat. Now the temperature changed. The temperature went from T initial equals to 300 Kelvin, right? It went to a final temperature that is 399 Kelvin, right? So there is a delta T, which is equal to T final minus T initial. So I'm going to define a ratio here. I'm going to call that ratio C, heat capacitance, and that's going to be equal to Q divided by delta T. Okay? So Q divided by delta T is a ratio that I'm defining, and this is the heat capacitance, and it's going to give me an idea of how much heat, how much energy I need to raise the temperature of a material by some amount. Okay, let's look at the PowerPoint slides here. And so we're going to say that the amount of energy that raises the temperature of 1 kilogram of a substance by 1 Kelvin, we're going to call that a specific heat. That is the specific heat. And so it is a definition, and it's a property of materials. Let me just try one thing here. Well, it is a property of materials. So specific heat, it is a property of material. So iron has a specific heat, copper has a different one, water would have a specific heat that is different from those other two. So now, if there is no work, like in the previous example, if there is no work, then the heat needed to bring about a temperature change delta T is given by, this is the heat needed, that is equal to the mass of the system times the specific heat times delta T. We can also define the molar specific heat, and the molar specific heat, by analogy, is just the amount of energy that you need to raise the temperature of 1 mole of a substance by 1 Kelvin. And again, the Q would be equal to the number of moles times C times delta T. So this quantity here is a very important quantity in thermodynamics. It's a quantity that is a property of each material, and we can measure that in the lab. That is a nice thing. So let's look at a question here to see if we are understanding these concepts. So two liquids A and B, they have equal masses and equal initial temperatures. Each is heated for the same length of time over identical burners. Afterwards, liquid A is hotter than liquid B. Which one has the larger specific heat? A, B, or there's not enough information? Just take a minute to answer that question. Well, the answer would be B. Remember, Q is equal to mc delta T, right? So each one receives the same amount of heat, and so the one that has the less delta T here have to have the greater C here. This table here shows a specific heat for different materials. So for aluminum is 900, and this is the specific heat in joules per kilograms per Kelvin, and this is the molar specific heat. So you have copper here, iron, gold, lead, ice. Compare ice with all this. What this means here is that it's very hard to raise the temperature of ice. For liquids, we have alcohol here, we have mercury and water. And again, water has a very high specific heat. That means it's very hard to raise the temperature of water. And that gives water a very nice property. Water works really well as a thermal bath. If you want to keep something at the same temperature, you put it in water, right? You put it in a swimming pool, and it's going to stay at that temperature for a long time. We have another question here. 1 kilogram of silver, and this is a specific heat, is heated to 100 degrees Celsius. It is then dropped into 1 kilogram of water, right, at 0 degree. And all this is insulated. After a short while, the common temperature of the water and silver is what? 0 degrees, between 0 and 50, 50 degrees, between 50 and 100, or 100 degrees Celsius. Take a minute to answer this question. Well, the answer is going to be between 0 and 50, and the reason is, well, you're going to need a lot more energy to raise the temperature of water than silver. So whatever extra energy silver had, most of it is going to go into the water, but that is not going to be enough to raise the water to at least 50 degrees, because you need a lot of energy for water. So it's going to be between 0 and 50 degrees.